Well, before everything we know, there was nothing. No stars, no planets, not even the space between them. And then, in an instant too small to measure, it all began. This single extraordinary moment is what we call the Big Bang. It is not an explosion in space, but the expansion of space itself from a point of unimaginable density and heat. This is our origin story, written in the language of physics and observed in the light from the most distant corners of our cosmos. It's a story we are still piecing together, one discovery at a time. Imagine all the energy, all the matter that would ever become galaxies and stars, or you, compressed into a region smaller than a single atom. From this state of pure potential, the universe began to unfurl. In the first fraction of a second, inflation took hold, a staggering exponential expansion. Space itself stretched faster than light. This incredible burst of growth smoothed out the universe, ironing out wrinkles. A quantum fluctuation became the grand arena of reality. The universe was incredibly hot and dense, a seething soup of fundamental particles, quarks, electrons, photons, colliding with immense energy. A featureless, glowing fog where the laws of physics were just taking shape. Within this fiery beginning lay the seeds of structure, complexity, and life. Expansion continued, and the universe began to cool. Energy congealed into matter, E equals mc squared. The fundamental forces of nature, gravity, electromagnetism, and the nuclear forces, separated from a single unified force, each beginning its role in shaping the cosmos. The universe journeyed from simple symmetry to the beautiful, complex asymmetry we see today. As the universe expanded and cooled, the frantic energy subsided. Just a few minutes after the Big Bang, the temperature dropped enough for quarks to bind together. They formed protons and neutrons. For a brief but crucial period, the universe was like the core of a giant star, a cosmic furnace forging nuclei. Big Bang nucleosynthesis, a pivotal moment creating raw materials for the future. Protons and neutrons fused, creating the lightest nuclei. Most became hydrogen, single proton nuclei. Some formed helium and trace amounts of lithium. The precise amounts we observe today match predictions with astonishing accuracy. As expansion cooled the cosmos, the furnace shut down, about 75% hydrogen, 25% helium. Heavier elements like carbon, oxygen, and iron would come later in stars. Within minutes, the universe's chemical makeup was set. Vast clouds of hydrogen, helium, and a sea of free electrons. Photons were trapped, making the universe a bright, featureless, opaque haze. For 380,000 years, it remained a hot fog until it cooled to about 3,000 Kelvin. Photons no longer knocked electrons free. Protons and electrons could finally bind. Stable atoms formed, hydrogen and helium. This is called recombination. The fog cleared, light broke free and began crossing the cosmos. That ancient light was stretched by expansion from visible wavelengths into microwaves. Today we detect a faint, uniform glow filling the entire sky, the cosmic microwave background. The CMB is our most important evidence for the Big Bang. Mapped by telescopes like the Planck satellite, it is remarkably uniform, with tiny temperature fluctuations, just 1 part in 100,000. These were the seeds of all future structure. After the CMB, the universe entered the cosmic dark ages, filled with neutral hydrogen and helium. Tiny overdensities drew in more material under gravity. Over millions of years, vast clouds formed and pockets collapsed. Compression heated cores until nuclear fusion ignited. The first stars were born. Light ended the dark ages. These first stars were giants, hundreds of times more massive than our sun. In their cores, they forged carbon, nitrogen, oxygen, even iron. Their short lives ended in supernovae, scattering heavy elements that fed new stars. Gravity gathered stars into clusters, then merged them into the first small galaxies. Over billions of years, they collided and grew into grand spirals and ellipticals, including the Milky Way. We observe their recession in redshift, space itself stretching. Around later generation stars, disks of gas and dust began to swirl. Tiny grains, carbon, silicon, iron, stuck together and grew by accretion. Pebbles became rocks, rocks became planetesimals, planetesimals became planets. Our solar system, and Earth, formed about 4.5 billion years ago. The elements forged in long-dead stars are the very stuff of us. Carbon in our DNA, calcium in our bones, iron in our blood. Our story is inseparable from the story of the universe. With telescopes, we look back in time, seeing galaxies as they were billions of years ago. We measure the faint, ancient glow of the cosmic microwave background. We use physics to model a universe springing from a single point. Simple laws birthing complexity. From a hot, uniform state to a cosmos of structure and beauty, we are part of this unfolding. And our awe keeps growing.